Welcome back, everybody. This is the section on paleoseismology for the Foundations of Science unit on earthquakes. And you can probably deconstruct paleoseismology as something meaning paleo, old, and seismology having to deal with deformation of the earth. So we're trying to figure out how do we determine when past earthquakes occurred and how big they are when they occurred. This is going to be critical to our knowledge of assessing the risk to the different places we're looking at in this unit. So last time we explored where do the largest earthquakes occur, and then we kind of asked the next question is where do the most risky earthquakes occur? That's what we're trying to get through in this talk. We could have a very large earthquake that occurs somewhere in the middle of nowhere, doesn't hurt anybody, doesn't pose a risk. This one we're looking at some places where there's a lot of people at risk. We really want to know basically as much as we can about the hazard side of this situation. And last time we defined risk as the intersection between hazard and vulnerability. You'll recall that hazard is the actual geophysical phenomenon like an earthquake or a tsunami or tropical cyclone or something like that. Vulnerability is the thing that can get in there and get hurt. So it's people, it's ecosystems, and that sort of thing. Buildings can be vulnerable to different types of hazards. And risk is the intersection between these two. We could also define risk as uncertainty. You can imagine if you knew exactly when an event was going to occur, then you could reduce the risk to the point of it being zero. And what we're talking about doing now is using paleoseismology to do as best we can is reducing the uncertainty of when that earthquake can occur and how big it'll be when it happens. Earthquake prediction has been really a holy grail in the field of seismology. Will we ever get to a point where we can say exactly when an earthquake is going to occur? Probably not. Can we constrain the timing and magnitude of an earthquake to a point where we can say within a certain amount of time period it's likelihood that we'll hit a certain magnitude earthquake and we can therefore plan for it? Tools we have at our disposal to work on earthquake prediction occur first and foremost with historical accounts. If we have a long historical record of a place like Japan where they've recorded lots and lots of earthquakes, we can get an idea of how frequently a given magnitude earthquake occurs. Frequency-magnitude relationship of earthquakes or any kind of hazard is the most important thing that scientists can give to planners to save lives. Second field we're going to look at is paleoseismology. This really gets into the geology of the thing, where historical accounts are fine, they only go back so far. If we need to go deeper, we have to go into the geologic record and understand some geology so we can start picking apart when the last earthquakes occurred and how big they were. Another way of detecting earthquakes perhaps in months or days before the earthquake occurs, and maybe even minutes, are what they call piezoelectric effects. This is when you actually stress rocks, they release some electrical fields, and those can be measured in different things or picked up by different sensors. One of those sensors can be something like animal behavior. Animals sometimes have different types of sensory organs that can pick up things like changes in the magnetic field that humans can't, and they could start freaking out, and that might be a warning of an earthquake. Problem is, animals could freak out anyway, so it's really hard to use them as an effective predictive tool. One thing that I was originally skeptical of, which came up a few years ago, largely after the Haiti earthquake, was P waves. The idea is the P waves, because they're the primary waves that get there faster than the surface waves, and certainly the shear waves, can actually be used as an early warning. We'll talk a little bit more about that as we go on. Okay, historical accounts. Really gave me fits that after the Haiti earthquake, a lot of people from the West said, wow, we didn't see it coming. Capital of Port-au-Prince, Haiti has been destroyed at least 3 times now by major earthquakes. First in 1751, where they swore they weren't going to rebuild, they were going to move it somewhere further away from the fault. Of course, they rebuilt anyways in 1770 and destroyed the town again. And then, of course, in 2010 was the last earthquake. Curiously, in this figure, they don't have 2010 as a major earthquake, but again, that earthquake actually happened a little bit to the west of Port-au-Prince, and it really wasn't that large a magnitude. Think about the actual hazard side of this equation. Magnitude 7 earthquake happened not directly under the city. Could have been worse. The vulnerable elements in Port-au-Prince are what made it a really impressive disaster. Some places there are not historical records. They kind of come out of the blue. In 1755, there's a massive earthquake, magnitude greater than 8, that hit Lisbon in Portugal, caused massive tsunamis that hit even parts of the Caribbean, and people say were actually responsible for kind of the beginning of the Enlightenment movement when people started looking at science in a different way. Another similar event, which we still don't fully understand, was the sequence of earthquakes ranging between magnitude 7 and magnitude 8 that hit New Madrid, Missouri between 1811 and 1812. Now, I stress Missouri because if we look at this area where this earthquake occurred, and the red area here is the area of shaking and that caused a lot of damage to structures, and the yellow area is the area that people felt shaking. This is nowhere near a plate boundary. We're sitting back saying, hey, all the big earthquakes occur at plate boundaries. This was probably pushing a magnitude 8.2 event that occurred nowhere near a plate boundary. So there can be surprise earthquakes. But we're going to go back to the west coast to look at a place where there is obviously a fault. This is the San Andreas Fault at Walls Creek in California. You can see it going across the middle of your screen there, and it's so obvious because you can actually see where a stream has been offset by the fault. The San Andreas is a right lateral fault. You can tell in this because the top part of the image goes to the right. We're actually looking to the east here. You can see north going off to the upper left corner. And you can see evidence of old drainages that cut through here also. Well, it turns out that the person who did some of the original work on this is a man named Kerry C., who works at Nanyang Technical University here in Singapore. What they did is they said, hey, what happens if we dig a hole, a really long trench across this fault, and then see if we can see evidence in the geologic record of past ruptures? This is an example not from the San Andreas Fault, but from somewhere in Spain, but you get the idea. You end up getting something that looks like this, and it's up to the geologist to unravel it. What we're going to do in our homework assignment this week is try to unravel some of these types of information, and I want to go through how this information can be unraveled right now. So this is an image of a fault scarp that occurred during a big earthquake, I believe in Nevada in the 1990s. It ruptured the surface. Not all earthquakes actually cause a surface rupture, but this one was nice and clean. And you can see how it caused a very nice, sharp-looking feature. Well, over the course of time, this feature can actually erode. Now, this is an image of an old scarp. It's not actually a fault scarp, but I'll explain it a little bit, where see how it's got kind of rounded corners? Well, if we can trace out what this topography looks like, and assume what it would look like when that scarp was formed, with much more sharper features like the previous image, we can actually use some relatively simple math to figure out how old this scarp is if we know something about the climate in this area and how fast things want to erode. This is that very simple math. I laugh because the equation at the top is a simple diffusion equation. This is something that is really important. It talks about how heat flows. It talks about how salt would diffuse in water. It's a really powerful equation. It does some simple predictions. To actually get to how this causes a slope to become more rounded involves a little bit of math, but you can see it's actually really quite simple plug and chug math. Yeah, it takes a lot, and to solve this equation I couldn't tell you how to do it, but luckily Andrews and Hanks solved this equation in 1985, and we can thus plug in the slope above the scarp, the slope of the scarp itself, and the slope below the scarp, and get an idea of how old this scarp is, how long it took the scarp to diffuse like this, if we know what they call the diffusion rate, which is that K. Curiously, this is an example from an offshore landslide. I think I told you guys that my research is on offshore landslides. One of the big challenges we have in that is trying to figure out how old these guys are. This is a picture of the Afen Slide offshore northern Scotland. It looks for all in the world like it could have happened yesterday, but it turns out it's over 3,000 years old. It doesn't rain underwater. That was the first line of my PhD thesis. I was kind of proud of that. So the diffusion rates down there are very low, so something could be around for thousands of years and look like it happened yesterday because there's nothing that's going to cause lots of erosion down there. Currents aren't that strong, and like I said, it doesn't rain, so what's going to knock it down? I thought it would be a good idea to use diffusion equation to figure out how old these slides are if we could get an idea of the diffusion rate underwater. So I made a little model that said, okay, we know that this slide here is 3,200 years old. Some guys went out there and did some dating of it, carbon-14 dating. So I can put that in my model. I assume the green line, which you look carefully, you can see there is the initial condition. The blue line is topography as we see it today. So at time 0, we're going to say this is what the scarp initially looked like. Now we're going to go back through time and use I made a very simple computer model using that previous equation. 1,600 years. 3,200 years is my best fit. If I keep going much past that, it goes a little bit lower and doesn't fit quite as well. So that's using a diffusion constant of 0.05 meters squared per 1,000 years. This is 10 to 100 times slower diffusion rate than anything you see on land. But, sorry, I digress.